Welcome to the next lecture. Now, in this lecture, we will study the Bpsk modulation. In particular, we will study its error performance and also receiver design. So, till now, we have done Bpsk modulation without noise. Now, we will assume that we have additive white Gaussian noise channel, which we have explained it in the lecture of information theory, what it means. So there is a Gaussian noise which corrupts the signal. Suppose Si of t is the Bpsk signal we represent, or even if we use any other constellation, Si t is the transmitted signal. This is the notation. W of t is the Gaussian noise process. See, actually, for understanding communication systems, we need the knowledge of random processes, and that is why we assume that you must have done a course on random process in your BTech. But to keep the discussion simple, and I know the varied background of various people, so we will not involve too much of random process in this course. So whatever we need, I will try to explain within the lectures, whatever knowledge of random process we need. So I will try to explain that much, not in a detail, but to the extent which we need in to understand some of the basic aspects of design of digital communication systems. So random process is a very simple thing if we define it empirically. If x is a random variable, in addition to being random, having some distribution, if x depends on time also, then the random variable which is time dependent is called random process, right? And we have also briefly shown you that there can be a stationary random process, white random process, like we have white and stationary Gaussian random process, which has a constant mean. Now, in addition to this, x of t, small x of t, is the received signal received at the receiver after getting corrupted by noise. Now, this Si of t is input, W of t is the noise, it gets added to the signal, and this is the channel model. Okay, additive wide Gaussian noise channel model. This we have already done. Now, what is the task of receiver? The task of receiver is that given x of t, after receiving x of t, receiver has to decide or guess what symbol was transmitted. Now, since it is corrupted with noise, so the task is full of errors also. So that is the what receiver has to. For example, in Bpsk case, what is a symbol? A symbol can be 0 or 1, or equivalently root e minus root e for 0 and plus root e for 1, line coding. Now, given x of t, receiver has to guess whether 0 was transmitted or 1 was transmitted, minus root e was transmitted or plus root e was transmitted. The information given to receiver is, it knows the noise characteristics, distribution of noise, and it knows input symbols. And now let's assume for Bpsk, we know that Si of t is root 2e by t cos of 2 pi fct. Fc is the carrier frequency. Okay. Now we can write it in another way to keep it simple. So we'll define these two symbols, Si. So I can write it as phi 1 of t also, right? Root eb phi 1 of t. Phi 1 of t is the unit energy carrier signal, root over 2 by tb cos of 2 pi fct. Okay, and I will define two symbols. Si I will write for plus minus root eb. So I will define S1. I will define S1 for plus root e. So whenever I transmit, basically I want to transmit symbols 1, binary symbol 1, I will be representing that by a level plus root e, that I represent by S1. S2 represents minus root eb. Okay, the level for binary number 0. So I can write x of t is Si of Si. Si is now this baseband symbol, phi 1 of t, which is the carrier, plus W of t. Now this is our channel model. Now if you see, to analyze receiver design from this is not easy because x of t is function of time, right? So what what we want to deduce the detector or the detection rule, we can say, given x of t and the knowledge of noise w of t. Since this uh, function of time, x of t is function of time, phi 1 of t is function of time, w of t is function of time, it will be difficult to deal with this. So we want to convert it into some simple problem. Okay, now what can we do? So we want to quantify basically error performance also. What is the error rate? And also we want to deduce the detection rule. So these are two things we want. We want to deduce the detection rule, how receiver should decide about 0 and 1, and what are the errors while making such decisions. What are the possible errors, and what is the error rate for that? Okay. So now you recall that this Si of t is in pass band, because we have modulated the signal, and S1, S2 they are the baseband representation. That is a message signal representation, low frequency representation. Okay, and this equation is also in passband, right? Now you recall that how we converted passband to baseband. Okay, so this is also passband. Noise also is here in passband, and of course x of t will definitely be in passband because Si phi 1 of t is there. Now we want to convert the whole equation into a very simple scalar type of equation. Now you recall that for Si of t, what we did is we multiplied it with phi 1 of t again. Okay, and then we integrated it, the correlation operation, and you know what we get Si phi 1 square t dt, right? Now this is unit energy, so it is equal to Si, right? Now we will do the same thing on both the sides. That is, we'll multiply x of t with phi 1 of t and integrate it to 0 to t. We will integrate this Si phi 1 of t with phi 1 of t again, so it becomes phi 1 of t square dt. We will integrate this noise also. Now see, I have told you that compare this with the vector operation. This correlation operation, that's integral x of t phi 1 of t, it is equivalent to a dot product of x of t and phi 1 of t. So what is the geometrical significance of dot product? Suppose you have a vector A and you take its dot product with any other vector, that has a geometrical significance of projection. Okay, suppose ijk are the usual unit vectors which form the orthonormal basis. Now if I take a dot I, okay, a dot I, it will give you the projection of the vector A in the direction of I, component of vector A in direction of I, right? Sorry. In general, dot product of any two vectors, suppose A dot B, that gives projection of A in direction of B or projection of B in direction of A. But here we are dealing with unit vector. Phi 1 is equal to unit vector. So the first thing is integral xt phi 1 of t is component of x of t in direction of phi 1 of t. It will be a scalar type thing. It's a projection of received signal x of t in direction of phi 1 of t. Let's represent it by x. It will not be the function of time because it is a projection. Because phi 1 of t is a orthonormal basis function. So let's represent by x. Okay, because we have even correlated, right? We have integrated 0 to t. Now the second thing is s1 phi 1 square, that is equal to si. Now the third thing is the integral of noise process. This is the w of t phi 1 of t dt. This is the projection of noise in direction of unit vector phi 1 of t, unit vector function. So it will be component of noise, right? So for a noise process, it is a component of noise. And since w of t is Gaussian, take this result without proof, that any component of noise in any direction will also be Gaussian. So this W, which is the projection of W of t in phi 1, is also Gaussian random variable. But now it doesn't depend on time. It is no more a process. It is a simple random variable. Now see, we have a beautiful scalar parameters. This is the Gaussian random variable. Let's take its mean 0 and variance we assume here sigma square. Normal, mean 0, variance sigma square. Now the complicated random process equation x of t is equal to si of t plus wt gets converted into scalar equation x is equal to si plus w. Now given x, we have to guess whether 0 was transmitted or 1 was transmitted. What is given to us? The knowledge of w. Now we assume this si, which takes value plus root eb minus root eb, it takes the value equally likely, that is with equal probability. Okay, equally likely symbols. So that is probability of si equal to root eb is same as probability of si equal to minus root eb, which is equal to half. Okay, this is called equally likely symbols. There can be unequal probability also. Now density function of noise is Gaussian density 1 over 2 pi root sigma square e to the power minus omega w square by 2 sigma square. Now what is this x? If you see conditioned on si, this x is also Gaussian. Okay, so here is our problem. Given x, we have to deduce or decide what was transmitted, whether 0 was transmitted or 1 was transmitted. Okay, so now to arrive at that, what are the things given to us? We just know the probability distributions, probability density of noise, and we know the probabilities of occurrence of symbols plus root eb minus root eb. So hence we need to deduce the probability distribution of x, probability density function of x. From that we can take some decision. Now let's first take its PDF as fx of x, right? It be the PDF of x, but we will mainly deal with its conditional probability, because definitely we have two scenarios: either si was root eb or si was minus root eb. Now conditioned on si, what is the probability density function of x, right? This will be very important quantity for us. Let's take example, if si is equal to, if it was equal to root eb, suppose we assume 1 was transmitted, that is si is equal to root eb. What will be conditional density of x given si is equal to root eb? Fx given si is equal to root eb, right? Since we have now fixed root eb, you look at the equation again, x is equal to si plus w. Now si is fixed, so w is the random variable here, which is Gaussian. So x is also Gaussian with a shifted mean, right? Mean of x will be root eb, because mean of w is 0. We assume Gaussian noise has 0 mean. So hence variance of x will remain same, because variance does not change if you shift the random variable. So hence x is a Gaussian random variable, mean root eb and variance sigma square. So I can write the density 1 over root 2 pi sigma square e to the power minus x minus root eb, because root eb is now mean. Okay, square divided by twice sigma square. So far so good. Now similarly the other possibility is that si is equal to minus root eb. In that case x will be Gaussian random variable with mean minus root eb. So I can write the density, conditional density function of x as 1 over root 2 pi sigma square, because variance is same, e to the power minus x plus root eb whole square divided by 2i sigma square. Okay, now see, we have to make a decision. So we can make decision only based on these probabilities, right? So what is the best decision rule actually we can have? So we have this x is equal to si plus w. Now what is the best decision rule we can have to decide, to arrive at detection rule that what was transmitted at the receiver? So the best decision rule will be to first to decide that binary 1 was transmitted. Suppose when you will decide 1 was transmitted, that is root EB was transmitted. You will decide it based on some probabilities. What is the probability? Probability that SI is equal to root EB. What is given to you? Conditioned on X, the noisy signal. If it is greater than probability that SI is equal to minus root EB conditioned on X, then you will decide that 1 was transmitted. This is the best you can do. Similarly, else you decide binary 0 was transmitted, that is minus root EB, but decide binary 0 was transmitted if it is reverse, that is probability of, if probability of SI is equal to minus root EB or plus root EB given X is less than probability of SI is equal to minus root EB given X. Okay. Now, these conditional probabilities are difficult. In fact, they are impossible to be computed. Right? Probability of SI given X, it is not possible to compute. You will realize it later. So we need to convert it into some computable conditional probabilities. You know which rule will help here? For to convert impossible conditional probabilities into the possible conditional probabilities. That is the famous Bayes rule, which forms a bridge. Okay, because computing this probability is difficult. Suppose uh, if I take instead of random variables for Bayes rule description, I will take sets A, B, C. Okay, and see one thing I will tell you: if Bayes rule were not there, we would not have moved next to next step, and we would not have any digital communication receiver, possible without Bayes rule. Now, what is Bayes rule? Suppose I take A and B two sets, and I will write their joint probability of A and B, which is equal to probability of A given B times probability of B. Also, it can be written as probability of B given A times probability of. This is Bayes rule. Now, you see, you have two conditional probabilities: probability of A given B in terms of probability of B given A. Whichever is difficult, you represent that in terms of whichever is easy. Now, let's suppose B is SI and A is X. So, probability of B given A is difficult to compute. So, I can write probability of B given A in terms of C, probability SI given X, probability of X is equal to probability of X given SI, probability of SI. So I can now express probability of SI given X in terms of probability of X given SI, because that probability is easy to compute, as we will demonstrate it soon. First of all, I can write decision rule in a compact way. Probability of SI given root EBX, if it is greater than probability of SI equal to minus root EB given X, then decide in favor of 1. I will write that at the top. If it is less than the right hand side, then it decides 0, that I will write 0. So this is the compact way of writing the decision rule. Okay, this is our decision rule, and we want to compute it. So for the receiver, it will help us in the design of the receiver, actually, to arrive at design, which we have done last time without noise. Now we apply Bayes rule for these conditional probabilities on both the sides, right? Because this is difficult to compute. Now, what will be on the left hand side? Probability of X given SI equal to root EB, right? Probability of SI equal to root EB. If it is greater than, so we can replace this probability actually with density function fx, right? Because it is a conditional variable, so it is density function. If it is greater than density function of x, probability of x, SI is equal to root EB minus root EB. Okay, actually it should be minus root EB. Correct? Then decide 1, else decide 0. Now, probability of SI, see this probability, fx SI give is equal to root EB is the Gaussian density, right? And so I will write it 1 over root 2 pi sigma square. This we have derived at the top, right? If a condition on SI is equal to root EB, this is the Gaussian density with mean root EB, wherein sigma square. This is half. We have assumed that the symbols occur equally likely, hence it is half. Okay, greater than. Oh, there is one more thing. There is divided by fx, probability of x, right? On the both sides in Bayes rule. I forgot to write that. But that will get cancelled because this fx does not depend upon the symbol transmitted. It is same on both the sides. Hence, this fx, that is the absolute probability density of x, it has no role in decision rule. So it will get cancelled on the both the sides. Okay, it is a common thing. So hence the decision rule is if this probability is greater than 1 over root 2 pi square. Now fx given si is equal to minus root e b is a Gaussian with mean minus root e b and the density, and probability of si is equal to minus root e is half gets cancelled, common factors get cancelled. We can take now logarithm on the both the sides. First of all, we get decision rule as if e to the power minus x minus root eb square divided by 2 sigma square is greater than e to the power minus x plus root eb squared divided by twice sigma square, then decide in favor of 1 else 0. Take log on the both sides. Log is a monotonic function, will not change inequality, so we will get if we take log natural with base e minus x minus root eb square divided by twice sigma square greater than minus x plus root eb divided by twice sigma square, then decide in favor of 1 else decide in favor of 0. Now if I multiply both sides by minus 1 so that minus disappears, the inequality gets reversed. You know that suppose if 2 is greater than 1, if I multiply minus 1, minus 2 will be less than minus 1. Similarly, if we have minus 1 greater than minus 2, right? So sorry, when we multiply minus 1 on the both the sides, what will we get? We'll definitely get that 1 is less than 2. So similarly here I multiply minus 1 on both the sides to get rid of this minus. I will get x minus root eb by 2 sigma square. Okay, this also gets cancelled. 2 sigma square is common. Is greater than, now x plus root eb, if it is greater than this, then decide about 0, right? It is reversed now, inequality, else 1. Here, this is the decision rule, one way of saying. People make mistake here, okay, usually. What mistake people can make? It is wrong. They will say that I will take square root on the both the sides and I get x minus root eb is, if it is greater than x plus root eb, decide 0 else 1, then x gets cancelled. We don't arrive at any rule. Okay, this is wrong. What is a mistake? When you take square root of anything, suppose square root of x, it is not equal to x, it is mod of x. So it is mod of x minus root eb if it is greater than x plus root eb square, decide 0 else 1. This is also very important form of decision rule. It says that suppose the constellation is this is the root eb, this is minus root eb baseband. Now this is what was transmitted. What will receiver receive? Receiver will receive the corrupted signal, right? To this root eb or minus root eb, noise is added. See si plus w, right? So what receiver will receive will lie on x-axis, but it will not lie exactly on the positions where it was transmitted. It may lie anywhere on the x-axis depending upon how noise. It can be here, it can be here, it can be here, it can be here, right? Now suppose it is here, this position. So how will receiver decide? It will take the distance of this x from root eb. This is what mod of x minus root eb means, taking distance of x from root eb, and it will see if this distance is greater than or less than the distance from minus root eb. Now in this case, in this particular case, it is less than. So hence receiver will decide in favor of 1. Otherwise it would have decided in favor of 0. This is called minimum distance rule. Okay. Now see, this Bayes rule got converted into a minimum distance rule. It's very important rule and it carries over to other higher modulation schemes also. Now there is another way to write decision rule. Let me take the squared version, x minus root eb whole square if it is greater than x plus root eb whole square. I will expand the square. It becomes x square plus eb minus 2 root ebx is greater than x square plus eb plus 2x root eb. X square eb are common, then decide in favor of 0 else 1. x square and this EB are common, they will go away. Now I will take this 2x root EB multiply, add on both sides, so I get 4x root EB. Now inequality will again reverse because I have shifted the term there. If it is greater than 0, then decide 1 else 0. Now 4 is a constant, root EB is positive thing, so the only thing which affects is the sign is x. So hence the decision rule is if x is greater than 0, decide 1, else decide 0. See, this is the decision rule. If you remember previous Bpsk symbol, we used this decision. We had a box on decision device, right? This is what decision device does. At that time, we assumed there is no noise, but even if there is a noise, decision rule does not change. What is the moral of decision rule? So when you receive x of t, convert that into x after doing the correlation, then just check the symbol of x. If it is greater than 0, decide 1 was transmitted. If it is less than 0, decide 0 was transmitted. But you see this decision rule, now probability of Si equal to root EB given x is and probability of Si is equal to minus root EB x. Actually, we are choosing the symbol for which probability is maximum, right? If probability of Si is equal to root EB given x is maximum, I will decide 1 was transmitted. If probability of Si is equal to minus root EB given x is maximum, I will decide 0 was transmitted. And argmax means that which symbol will maximize the probability. Okay, that is called argmax. Suppose if probability of Si is equal to root EB given x, if this is maximum, then I will choose argmax as I, where I is the, suppose S1, so I is equal to 1, I is equal to means S2. Okay, 0 was transmitted. Since this decision rule chooses the symbol which has maximum probability, or in other words we say maximum likelihood. Okay, so this is a likelihood. Similarly, fx x given fx of s given root EB or minus root EB, this is also likelihood. So we are choosing a symbol with maximum likelihood. Hence, this rule is also called maximum likelihood decision rule. And the receiver designed based on this is maximum likelihood receiver. This is the maximum likelihood rule. This also, because we got it from maximum by taking maximum of the probabilities. This decision rule. Okay, it's the best, one of the best receivers we can have, the best we can do. ML receiver. Okay, maximum likelihood receiver for BPSK. Okay, so what we had done in previous lecture is actually maximum likelihood receiver for BPSK modulation. Now see, definitely there is a possibility of errors, right? Because noise may affect symbol in such a way that you are arriving at a wrong conclusion. So we need to compute that probability of error. So there can be two types of errors, two possible errors in especially in case of BPSK modulation. One is that uh, we decided in favor of receiver, took a decision that receiver decided that 1 was transmitted, but actually 0 was transmitted at the transmitter. Noise was so bad that receiver took a wrong decision. Or the other possible error is receiver decided that 0 was transmitted, but actually 1 was transmitted at the transmitter. These are two possible errors. They are symmetrical errors. Okay, so we will take one of them. Let's take the first one, probability of error as probability receiver decided 1. When will receiver decide 1? When x is greater than 0. You see here, decision rule. So x greater than 0 is equivalent to saying receiver decided 1. Given 0 was transmitted, what does that mean mathematically? That Si is equal to minus root EB, because that is the level coding for 0. Now we need to compute this probability. So what is x? X is Si plus W greater than 0, conditioned on Si is equal to minus root EB. Now what I will do is, since it is conditional Si is equal to minus root EB, I will put that value here, Si is equal to minus root EB plus W greater than 0. Conditioning now disappears. This is same as probability W given as root EB. You know W is Gaussian random variable with a given density. So we can write it as root EB to infinity, then PDF of Gaussian 1 over root 2 pi sigma square e to the power minus W square by 2 sigma square dW, right? But this probability this integral is impossible to be computed. So people have made numerical tables of this. For that, we will define a special function of this type which is called Q function. Now, what is Q function? Suppose we take a random variable z which is of zero mean and unit variance. This is called a standard normal random variable or standard Gaussian random variable. When there is mean 0, variance 1, it is called a standard random variable. Okay. Now let's ask a question that what is the probability that this standard normal random variable z is greater than some particular value small z. Okay. That is the definition of Q function. It is function of small z, it is Q function. In terms of integral z to infinity, 1 over root 2 pi e to the power minus some z dash square divided by 2. I had used dummy variable here. Don't use z for integral also, z dash. Okay. Now, but suppose we have a random variable which is not zero mean and unit variance. Suppose y is a random variable which is having mean mu and variance sigma square. And I have a similar question about y. Okay. Sorry. So I have a similar question about y. What is that probability? Y is greater than small y. Now I have to first convert it into standard normal variable. For that, what should we do? First, subtract the mean on both sides. Y minus mu greater than y minus mu. Now look at the y minus mu. This y minus mu has mean 0. Why? Because expected value of y minus mu is expected value of y minus mu. This is mu minus mu, which is 0. So we got mean 0. But we should also get on the left hand side variance 1. How to get variance 1? See, y has a variance sigma square, hence y minus mu has also variance sigma square because it doesn't change the variance shifting. Now to get variance 1, I should do y minus mu divided by sigma. You see what will happen greater than y minus mu divided by sigma. Now see the variance of y minus mu by sigma. Variance of ax is equal to a square variance of x. You know that. So variance of y minus y by sigma is 1 by sigma square variance of y minus sigma. Okay, so variance of y minus sigma is sigma square, which gets cancelled is 1. So now y minus mu by sigma is same as z, standard random variable, greater than y minus mu by sigma. Now this is a Q function of small y minus mu by sigma because that comes in place of small z. So it is a Q of y minus mu by sigma, and this can be computed using tables. Tables have been prepared for Q functions. Okay, we can easily compute, and we have MATLAB functions for it now. Now what is the probability of error? Probability of error, we go back to this, is W random, that is Gaussian random variable greater than root EB. Now see, W is a Gaussian random variable, mean is 0, but variance is sigma square. So to convert it into standard form, we don't need to subtract mean because already 0. We just need to divide by the sigma, right? Because variance of W is sigma square. So we get W by sigma greater than root EB by sigma. Now W by sigma is same as Z because W by sigma is having 0 mean and unit variance, right? It is same as Z, 0, 1. So I can write as probability, this is equal to probability Z greater than root EB by sigma. See, mind it, this is not given in the book in this way, simple way, so note it down. This is equal to Q of root EB by sigma because instead of small z comes this root EB by sigma. Now this can be computed using MATLAB. Now, in previous lecture, we denoted power spectral density to be n naught by 2, and also we said that this is the variance of the Gaussian random process, if you remember. So we define the sigma square to be equal to n naught by sigma to be root n naught by 2, right? So hence I can write this probability of error as 2EB divided by n naught. This is the probability of error for Bpsk symbol in presence of Gaussian noise. There is another way of writing it. EB by n naught by 2 can also be defined as signal to noise ratio because EB is the signal energy and n naught by 2 is related to the noise energy, right? EB is the bit energy, n naught by 2 related to noise energy. So the ratio of EB by n naught by 2 can be defined as SNR, signal to noise ratio. Hence we can write probability of error to be equal to Q of under root of SNR, right? And we can plot this function. It is exponentially decreasing. You can use MATLAB function also to plot it. It is exponentially decreasing with SNR. Okay, as SNR increases, probability of error decreases exponentially. Sorry. Now there is approximation of q of x given in the books. It's approximately equal to e to the power minus x squared by 2. So probability of error is approximately equal to e to the power minus SNR by 2. Again, this gives the same behavior, exponentially decreasing behavior. Okay. Now the same technique we have used for Bpsk, it can be used for computing probability of error for Qpsk and higher modulation schemes that I will show you in subsequent lectures. Okay. So if you follow these steps, absolutely the same steps will be followed for other higher modulation schemes also. If you understand BPSK bit error rate performance, you can easily understand the BP for QPSK, for MPSK and MQAM.